I'm going to introduce our next speaker. Speaker is on the screen and almost needs no introduction to all of you, but I still do. Daan Crommelin, Professor Emeritus, Utrecht University, former Scientific Director, Top Institute Pharma, advises venture capital on investments, and also expert witness in several patent litigations. Daan, the floor is yours.
Thanks, John. It's always a pleasure being here. Bea, thanks for inviting me. Well, let's go to the topic. The stability of mRNA vaccines and therapeutics, not a cold case. Not a cold case, of course, refers to the fact that we have to store these vaccines at minus 80 or minus 20 degrees centigrade with all the complications there. And if we don't do that, these vaccines are inactivated very fast. These two gentlemen are my sparring partners or sounding board, and when I come up with some stupid idea, then they point it out to me, and I just forget about it. Everything I'm going to say is on these review papers. The one on the right bottom is an interesting one, and we published that 2.5 years ago, and there are already 650 plus citations, which is quite unusual for publications from my hand, but well, sometimes that happens. So in other words, look them up, and there's much more than I can discuss in the next 12 minutes. What are we talking about? The mRNA molecule structure. Linear nucleic acid polymers to 1,000 nucleotides. Actually, the spike protein of COVID is 4,000 plus nucleotides. So large molecules with a CDS. The CDS is the coding sequence. The UTR is the untranslated regions and the two cap regions. What is often forgotten is that these mRNAs, and you saw that this morning also, it came as a threat, but basically they are very folded in a very complex way with 3D heterogeneity as shown on the right. So I come back to that. This folding story is very important also as far as the stability is concerned. They are large molecules, 10 times as large as the protein that they generate. So that is a number of characteristics for the mRNA. But what is very important is on the bottom, one break in the mRNA chain, and there is no action. You lose all the action just by one break somewhere. And that is different, for instance, than you see with monoclonal antibodies, where typically 70% of the monoclonal antibody is the main product, and the rest is deamidated or double deamidated molecules that are still active, and nobody really is hurt. One break in the chain and it is over. The second part of the family is of these vaccines are the ionizable cationic lipids, alpha lipids, PEG, and I would draw your attention in particular to the ionizable cationic lipids because that plays a role later on in my story. Just as an aside, of course, we are very happy that the Nobel Prizes were awarded to excellent scientists who worked on the mRNA and to reduce the immunogenicity of the mRNA. But what would this invention or these ideas, what would they have meant if there wouldn't have been LNPs around? So wouldn't that have been a nice opportunity to honor the drug delivery field, in particular the LNP field, and I have a candidate in mind that I'm not going to mention here. But it is a lost chance, I think. Yeah, thank you. I think that is correct. Nothing bad about the winners, by the way. Nothing. But the Swedish committee should have thought a little bit further than that. Anyway, is there a problem that when you go to the literature and try to figure out what the stability issue actually is, there is very little of hard data around. And this is from the Moderne Science and Technology Day last year. And they show here minus 25 and 25 degrees for, I mean, I think these are particularly meant for lawyers, so they don't put any indication of on the y-axis and the x-axis what it means, but it shows clearly that there is an stability effect. So we are not talking about something that is surreal or academic. Before I'm going to mention some typical issues around stability on storage, the purity of the original product is something to really have a good look at. And here you see some work by Patel on the bottom. He is a Pfizer, from a Pfizer group, and they published this paper this year. On the top left, peak 1, peak 2. Peak 2 is intact mRNA, peak 1 is degradation product. And on the B panel, you see that the peak 1 is the blue arrow, and peak 2 from the top, I don't know what is it, red arrow. I'm colorblind, so I can't see that. But anyway, the other arrow is indicating that this peak 1 it consists of a lot of degradation products already. So it's very important to realize that at the beginning of your journey to prepare these vaccines, that you make sure that you have the proper purity there. And I think Pfizer did a good job to sort of point that out. The question is, of course, what does that mean? Why is peak 1? What, is that an issue, yes or no? Are these shorter mRNAs, are they translated, yes or no? And if they are translated, are they immunogenic? Well, they did some work on that, and that is shown on this slide. The top panel indicates the degradation, there's stress degradation there of the mRNA, and then they put the partially degraded mRNA on the gel, and you see the blue arrow indicates translated protein, and you see that disappears over time. It goes from 0 to 10 minutes degradation. The protein disappears, and no other proteins show up, and that is for the authors of this publication a sign that the short degraded mRNAs from the beginning, that they are not translated, so you don't run this risk of immunogenicity. There's something to say about that, but let's move on. I will focus today only on the mRNA degradation and not on the LNPs in general, and only on the chemistry. I talk about hydrolysis and I talk about tertiary amine oxidation reaction products, and the rest, forget about it. And here, this is indicated again in more detail. I'm talking about the transesterification, in other words, the hydrolysis of the phosphate and the adduct with an electrophile and aldehyde. Those are the two reactions that I'm going to talk in the framework of the degradation of mRNA. So let's first have a look what you can do. I mean, what are the means you have to stabilize your mRNA? Are you totally without any tools? Here I show you in black the ones that I'm not going to talk about, in red a few that I'm going to talk about. First of all, I'm Nobel Prize worthy. Selecting of modified nucleotides and not only decreases the immunogenicity, but also is supposed to increase stability. There are questions there, but supposed to increase stability. Then increasing the GC content, that's an old trick to stabilize mRNA. Another way to do it is to look, as I already sort of introduced, look at the secondary structure, so the third bullet from top, minimizing the average unpaired probability. In other words, the AUP. In other words, the more you condense the mRNA, the more stable it is. And that is, there are algorithms to take care of that. Chain length, I mean, if you shorten the chain length, you reduce the chance that degradation occurs. And last but not least, purity level optimization of the mRNA drug substance. That is another issue that I sort of refer to. Well, that is worked out in a little more detail on this slide. Here you see the nucleotide or nucleoside modified RNA introduce the pseudo uridine or the 5-methyl cytidine are ways to increase stability according to some. Another way to do it is increase the GC motifs. They increase the structural stability by the base stacking induction. And then what else? Oh, then we're talking about on the right-hand side, do as much as you can to form these secondary structures. And the Stanford group, publication by Lappick and Wayman Steele on the bottom here, they clearly design mRNA molecules that have a maximum secondary structure. So the base stacking is maximum, and that induces stability. Well, here again from the Moderna Science and Technology Day, I mentioned that if you shorten the mRNA molecule, then you increase automatically the stability. And I even had to correct the y-axis in this case. But you see that when you look at the stability, the y-axis is a stability-related parameter. You see that the shorter the mRNA, the higher the stability. In other words, shortening of the mRNA helps you in stabilizing the molecule. The last few minutes on not on the mRNA as an inductor of an inductor of the instability, but as a victim of degradation reactions. And this is a publication, excellent publication by Meredith Packer from Moderna, a novel mechanism for the loss of mRNA activity in lipid nanoparticle delivery systems. Well, I read it, and basically what they found is that the cationic lipids cause adducts to the mRNA. And I'll read it now so that you get the text, exact text. Specifically, electrophilic impurities derived from the ionizable cationic lipid components are shown to be responsible for this loss of mRNA activity. Mechanisms implicated in the formation of reactive species include oxidation and subsequent hydrolysis of the tetraamine. And basically, you get aldehydes. And the aldehydes interact with the bases of the mRNA. So their conclusion is it does remains critical to ensure robust analytical methods and stringent manufacturing control to ensure mRNA stability and high activity in LNP delivery systems by using very pure cationic lipids. So the cationic lipids should really be oxygen-free. Otherwise, you get these adducts. Well, and then there's an interesting relationship with real life because dual-purpose tris. Tris is a buffer and a hydroxyl radical scavenger, aldehyde sink, and that is what the chemical reaction here shows. Pfizer had, until the mid of the 2022, I think, had phosphate buffer as a buffer in their vaccines. And then all of a sudden, they changed that to tris. Moderna had all the time tris buffer in its product. So interestingly, Pfizer changed from phosphate to tris. Tris is, as you can see in the top, an aldehyde sink, picks up the aldehyde, no adduct of the mRNA, no instability there. So what happened? The shelf life of the Pfizer product was extended from 1 month to 10 weeks. So you see, science sometimes works and has an effect. Sometimes. Well, having said that, I think it's time to come to a conclusion regarding the mRNA LNPs. Can undergo different chemical degradation reactions. It is clear several strategies are out there to enhance intrinsic chemical stability. In other words, we are not without tools. And I only talked about the chemical approaches. There are also physical approaches to stabilize these products. And last but not least, impurities in the lipids may have a detrimental effect. And I notice now that I have 1 second left, and that's over. Thank you very much, and look things up in your presentation.
Thank you very much, Daan, for a great overview of the recent literature and your findings.